Okay, let's get started. Before I start, just out of curiosity, how many people made it to the conference this week to ISSCC? Okay, that's good. That's really good. I think it's a really good conference. There's a lot of interesting things. If you didn't have a chance to go, I think going to the conference is only half the story. The other half is actually looking at the papers. So I highly encourage you guys to get a hold of the proceedings of the conference and look through the papers. It's a great way to get motivated, research ideas. It's a great way to see what other people are doing, what the state of the art is, what's achievable. It's, for the most part, a very high quality conference, so I think you'll be very impressed. And certainly don't expect to go through the proceedings in one afternoon. It's going to take several weeks of, and really do encourage you guys to look through all the papers. So basically look at every page of the proceedings. The reason is that looks can be deceiving. For instance, if you look at, there's a couple of sessions on biological circuits or, silicon ICs for biology. And so you might say, okay, that has nothing to do with my research. But if you actually look at those papers, a lot of them are analog circuits. They're amplifiers, transimpedance amplifiers, or instrumentation amplifiers. So definitely there's little nuggets of circuits in every paper, and I encourage you to, when you're looking at each paper, to ask yourself, what's interesting about this paper? Why did it get in? What are they showing here? Why is it just performance, or is it something novel, or is it technology? So you have to really read these papers as a researcher to try to figure out what's interesting. And I guarantee you that if you go and do that with, let's say, even 50% of the proceedings, you'll come out with 5 or 6 research ideas. If you don't, then maybe you shouldn't think about doing circuits as your PhD. Truly, it is inspiring. Just another quick note. I know some of you didn't go because of cost reasons. Unfortunately, this year the ISSCC was more expensive for students than previous years. That's too bad. It's too bad that you guys didn't go because of the money. But definitely go next year and have your advisor pick up the tab. I know some of you are still looking for advisors, so that's hopefully something that will remedy very quickly. Okay. Let me just get another show of hands because a lot of people came in late. How many people made it to the conference? Okay, that's pretty good. So maybe about half. Okay, just a couple other notes. Because of the conference, a couple of people asked me to delay the homework, so the homework is now due on Tuesday. I don't think you really need the model files for this homework, but just another note, someone pointed out to me that there are a couple of bugs in the new model that I posted, and I corrected that last night, and hopefully it's okay now. So if you did download the new version of the model, download it again to get the most up-to-date version. Okay. Questions or comments? Okay, so let's get back on track with the lecture. You'll notice that the actual lecture number does not correspond to the lecture number here. It's kind of difficult for me to predict how much material we'll get through on a given lecture, and we've been going slower than I expected, which is actually a good thing. Given the reviews I read for the previous class I taught, almost everybody put down too fast, too fast. So I'm making a real effort in this class to slow down, and I hope that's showing. Okay, so this is where we were last lecture. We started talking about equivalent noise generators, and the idea is that if you have a two-port circuit, this could be an amplifier, it could be several amplifier stages. Even if you put down the simple equivalent circuit for each transistor, you're going to have 2 or 3 noise sources per transistor, and so it's going to turn into a pretty ugly beast. You're going to have 20 different noise sources, and how do you really tell what's going on in the circuit? So one way to compress that information is to transform your circuit into a noiseless 2-port and have equivalent noise generators at the input. And in general, these noise generators are correlated, and the correlation coefficient can be complex. So really, you can characterize the noise properties of a 2-port with 4 numbers at any given frequency, right? And these are frequency dependent. And the procedure for doing this is as follows. So I could just draw this for you here. It might be easier to see on paper. So I have my noisy 2-port, and let's say I short the input, and I measure, let's say I observe the output voltage noise. And then I do the same thing for the equivalent. So this is the noisy 2-port, and this is the noiseless 2-port. So for the noiseless 2-port, I have an equivalent current generator and an equivalent voltage. And if I short the input, you can see that this current source basically gets shorted. So none of the current noise actually goes into our 2-port. Only the voltage noise is excited. So let's call this Vn squared. So again, I can calculate V output noise squared here, and basically these two quantities have to equal each other. And if I equate them, I can calculate the equivalent noise Vn, right? So this is a function of Vn squared only. This here is a function of basically Vni, Ini. Basically, these are where I ranges through all the noise voltages and currents in our circuit. And so then we'll have an expression for Vin as a function of the internal noise sources. And now you can see I can play the same trick again and leave the input open. If I leave the input open, this noise source here is just dangling. It's not really impressing a voltage upon my 2-port. And so now the output in this case is only a function of In squared. And again, I equate this to the open circuit voltage for the noisy 2-port. There's open circuit, calculate VON again. This again is going to be a function of same thing as before, not with the same coefficients, but it's going to be some linear superposition of all the internal noise sources. And if I equate these two things, then I can calculate the equivalent input noise current. Okay? And now you immediately see that because the noise current and the noise voltage are a function of potentially some of the same internal noise sources, there will be correlation between the noise current and the noise voltage. Okay? Any questions on that? Okay. Well, one of the nice things about this formulation is that it allows us to examine the role of source resistance. In other words, you might be a user of an amplifier, and you want to know, for instance, if I have a given source resistance, what's the best amplifier to select? Okay, and a good example of that would be, let's say you're designing some sensor that inherently picks up current signals, and you want to convert that to a voltage so that you can digitize it. So now you say, okay, I need to build an amplifier to take this current. Let me just draw a picture. So let's say this is our signal current, and it has some source impedance. And let's say the signal current is very tiny. Let's say it's on the order of 10 microvolts. So I want to pick an amplifier so that at the output, the SNR is maximized. In other words, I want to amplify this signal without adding too much noise. So then the question becomes, what amplifier should I pick? And in general, if I go and buy an amplifier, it's going to be characterized with an equivalent input noise and input current. And let's neglect the correlation for now. Let's just assume these are, for the most part, uncorrelated. So then the question becomes, all right, what's your source impedance? Okay, and this is something that you might not have control over, right? It might be some kind of transducer sensor that has, let's say, a source resistance of 100 kiloohms. Very high source resistance. So in that case, how would you select your amplifier? What criteria would you probably use? Okay, let's get somebody who didn't take 142, because the 142 people probably know this. Anybody want to take a stab at it? So let me clarify. Let's say you had two amplifiers. I'll make this really easy for you guys. And amp number 1 and 2 have the same equivalent noise voltage. But amp number 1, so let's say VN1 is equal to VN2. But let's say amp number 1 has a higher current noise. Well, then it's really obvious, right? It created a really bad example. Let's say it's like this. Let's say amp number 1 has better voltage noise, but amp number 2 has better current noise. Okay? How would you go about picking these amplifiers for this particular application? So with this source resistance of 100 k ohms, which is going to be more important, the voltage noise or the current noise? Current noise, that's right. Yeah, why is that? You use the mic if you want to answer.
Because when you do the equation, you kind of short the Vn square, and then you do the stuff and find out the voltage on the input node is going to be high.
Well, here's one simple way to look at it. I mean, 100K is almost an open circuit, right? So this voltage noise, even if I have a low input impedance on my amplifier, is going to generate a current signal, which is Vn over Rs plus Zin. Rs is very large, so it's going to generate a very small current. So since my signal is a current, right, it's really the current that matters here. And we can make this more quantitative in a second. Whereas this guy, because this is such a high impedance, is probably going to go all into the amplifier, right? From current division rule, input impedance is low if it's a good current amplifier, so most of the current noise is going to go into the amplifier. Voltage division rule, since the input impedance is small, you're going to have a very small input voltage generated by Vn squared. Okay? So definitely we want to take amp number 2 in this particular case. Yes, question?
Yeah, is the fact that the sensor in this case is a current source, it's not very relevant because the...
You're right, yeah. That's a good point. It's really the source impedance, because you can always Thevenin transform, Norton Thevenin transform. So what really matters is the source resistance. Thanks for clarifying that. Yeah, it's a good point. Okay, so let's come back to the slide, and now we can see that this makes a little bit of sense. So the first observation is if the source resistance is 0, or let's say very low source resistance, then the voltage noise matters. That's much more important. And likewise, if the source impedance is infinite, then it's the current noise that really matters. But what happens, in general? What happens for an arbitrary case? So we'll look at that. Just another point in terms of MOS amplifiers versus BJT amplifiers. One of the nice things about a MOS amplifier is that the input current noise is very small, right? Because you have the insulated gate. So the only input current noise you have at low frequencies is basically your shot noise, which is due to tunneling current flowing in that device. That's very small. So that would be a good amplifier to use if you had a high source resistance. On the flip side, a bipolar device has lower voltage input noise because most of that noise is due to the base shot current, whereas the voltage noise is just due to the base resistance, which you can make small by making a big layout for your transistor. Okay? So given that simple observation, it's now clear, you have two extreme cases where you know the answer. What about for an arbitrary source resistance? Well, it turns out that for a given source resistance, there is an optimal amplifier out there. Or if you turn that around, for a given amplifier, there's an optimum source resistance. And that's what we want to find out. Okay? And the way to do this calculation to find the optimum is very easy. You just find the total output noise, take its derivative with respect to the source resistance, and set it equal to 0, solve, that's your optimum source resistance, verify that it's actually a minimum and not a maximum, you're not shooting yourself in the foot, and then you're done. And I won't bother doing this calculation because I think we could just talk through it. So this is the total output noise, and you can see that this voltage noise gets amplified by the voltage gain times an impedance, basically a voltage division, where Rin is the input resistance of the amplifier. So this Vin sees voltage divider times voltage gain. So does the noise due to the source, right? They're in series, so it's the exact same transfer function. For the current noise, we have something similar going on. So if I want to use the voltage gain instead of the current gain, I can observe that, first of all, some fraction of the current is going to flow into Rs and create a voltage. So that's In squared times Rs squared. And then that is going to get a voltage gain as well. Well, what fraction flows into Rs? Well, that's a current division. And the current division exactly works out to be the same ratio, because now it's the current going to the left as opposed to the voltage going to the right. So you see several terms in common. And so you can basically collect all these terms, and you can see that the total noise is Vn squared plus Vrs squared plus In squared times Rs squared. And now it's very clear what role Rs plays, right? You can set Rs equal to 0. In disappears from this equation. You can set it equal to infinity, and you can see that In dominates the equation. Okay, so now if I had done the same calculation with my, basically my, well, okay, never mind. So if you look at this equation for a little bit, you can see that this term here just looks like a noise source in series here. So in fact, I can even further simplify my model and say that I just have one voltage noise, let's call it V equivalent, and it has a value of Vn squared plus In squared Rs squared, and that's really the total noise from this two-port. That represents the total noise from the two-port. And so now all I have to do is compare V equivalent to VRS, the voltage noise from the source, to find out what's the best amplifier to use in a general situation. Okay? Now just one reminder is we have ignored the effect of correlation. Okay? So if you look at this calculation, we're assuming that Vn and In are not correlated, and that simplifies things. We'll come back and look at the correlated case in a couple of slides, but just keep that in mind for this result. Okay? Does this make sense? Any questions? What we've done up to here? Yes, Debo.
So it's not exactly related to the source resistance, but in general, in any amplifier circuit, it confused me last semester also, like if we have any biasing resistor or something that generates some noise, so is it good to have a large value of it or small value? Because it confused me of, like, if I look at voltage noise or current noise, it's in series with the gate.
Yeah, you have to, again, there's no magic bullet answer. It depends on the case. So for instance, if I had kind of like a discrete biasing scheme like this, right? Then the equivalent circuit for this circuit here is just a resistor to ground, right? It's a parallel combination. And so that means that the equivalent noise I can represent as a current noise like this, right? So if I want to minimize the current noise due to this, I make these resistors as large as possible, right? So you have to look at it a case-by-case basis, yeah. So this result, going back to just this result here, notice that this is not a universal result for the amplifier, right? Because it depends on source resistance. So this is why if you look in a data sheet, the manufacturer won't specify V equivalent. That would be why not just give one number, right? Why give two numbers? Well, they have to give you two numbers because they don't know what source resistance you're going to use. So they give you two numbers. Okay? Any other questions? All right, so, yes, good.
Question. I just want to know how they do the measurement for the Vn square and In square.
Okay, it's basically kind of a difficult thing to describe, but I'll just give you a quick overview and talk about it in more detail in office hours. what you do is you measure the noise figure of an amplifier as a function of the source resistance. So you vary the source resistance and measure the noise figure, and you find the optimum source resistance that gives you the minimum noise figure. And once you know the minimum noise figure and the optimum source resistance, that's equivalent to Vn and In. So you can transform from Vn In to, so for those of you guys who took 142, this terminology is going to be familiar. Those of you who haven't, it won't be, so don't worry. So there's going to be Z opt and NF min. And this is basically equivalent to Vn squared, In squared, and the correlation between Vn and In. And that's because basically Z opt is also complex, right, in a general case. All right. So if we go back to the slides here, you can actually do that simple math and find what the optimum source resistance is for your 2-port, and it works out to be square root of Vn squared over In squared. It's kind of a nice intuitive result, right? Because if the amplifier has, let's say, In equal to 0, then this ratio gives us an R opt of infinity. Why is that? Because if In is equal to 0, then I just have Vin, right? And this is my amplifier. And if I make Rs very, very large, then this voltage can't really excite a current in this loop, right? Or equivalently, the voltage division here with Rin is going to be 0. Which is nice, and there's no current to worry about, right? The other extreme also you can see makes sense. If Vn is equal to 0 and In is non-zero, then I want my source impedance to be 0, so I shunt all the current noise to the input, and none of it gets into my amplifier, right? And in general, for the general case, you have this nice result that the ratio of Vn to In is actually the optimum source resistance squared. So you can take an amplifier manufacturer's data sheet, look at their Vn and In, take the ratio, and that's the source resistance you should drive your system with, right? And if that ratio turns out to be different from the source impedance that you actually have, you should do an impedance transformation. So let me go back to this example. Let's say I calculate that Rs opt is 500 ohms. And going back to that same example, my source impedance was 100K. And so if I'm going to use this amplifier that has this Vn and In, I get really bad performance because 100K is very far from 500 ohms. So what I would like to do is to somehow transform the impedance so that looking here, I see 500 ohms. So I choose a transformer ratio that's 100K over 500 square root. Okay? Yes?
The case where In equals 0, the optimal R opt is infinity, and so on for the Vn equals 0. During those cases, the gain, the amplification is also 0, right? There's no input signal at all. The input is shorted essentially for one case, or the open circuit in the other case.
No, that's not true. So let's look at that case. So let's take the example that you gave. Let's say In is equal to 0. So I just have Vn, right? So then I drive my system with a very large source impedance, right? So this is my signal. So this is Rs. So effectively this Vin, as Rs goes to infinity, it just disappears, right? So Vin can't generate an input voltage over here. But my signal, Is, goes into my amplifier. And so basically I want to have either a transresistance amplifier or a current, some kind of current to current or current to voltage amplifier. That makes sense? Okay. All right, so let's get back to the slides. What happens when you have correlation? Okay, and the case with correlation you can also handle using a very nice trick. So the idea is, actually it's probably better to do this on paper. So I have V in and I have I in, and these are correlated quantities. So what I do is I actually split my current, or if you like you could do the voltage, into two components. I call it I correlated and I uncorrelated. If you like a vector, a graphical analogy, think of these two things as vectors, right? And because they're correlated, that means they have a component in common. So what I do, so this could be V in, this could be I in. What I would like to do is split I in into two components. I correlated, this is this component, and IU, which is perpendicular. Okay? So if I do that, then all the calculations get simple again, because if I take basically the dot product between V in and I in, that's the dot product between V in, IC, and IU. V in and IC are totally correlated, and V in and IU are totally uncorrelated. So this term is 0, and let me just call the correlation coefficient YC. Question?
Like here the diagram seems somewhat like if you should have split it in phase with Vn and perpendicular to Vn.
Yeah, I did it the other way actually. I split V instead of splitting I. But you guys get the point. Yeah. Let's redraw this picture. Thanks for pointing that out. So this is V in, this is I in. So I want to split I. So this is one component, and this is the other component. So this is IU, and this is IC. Actually, this picture was nicer. Should have done it the other way. Okay, so with this background, if you go through and redo the math that we did on the other page, and I won't bore you guys with this, and I'll just give you the result and encourage you to look at it. Let's go back to the slides. This is the result that you get. You recalculate that V equivalent, and now you have this extra term, YC times ZS. As the correlation goes to 0, you get back the same answer that we had on the previous page. In general, you see that there is this extra term here. Okay? And again, so now given this is the voltage, we can calculate the variance of this voltage, and we get this expression. And now we do the math again to try to find the optimum source impedance. This time it's an optimum impedance, so I have to find the real part and the imaginary part. And this is the result. The result is that the real part is the same expression we derived previously, plus this extra term due to the correlation, and the imaginary part is just due to the imaginary part of the correlation.
Yeah, question. I just don't get what is YC and ZS? Was there a physical meaning there?
So ZS is a source impedance. YC is a correlation admittance. It's basically I take the dot product between the voltage and the current, and I get a number. And I just observe that I can define that as if, so I could basically write, so let me come back here. So I have I in is IC plus IU. I'm going to write IC as YC times V in, because this is completely correlated to V in. And so now when I take the dot product, you can see I get YC Vn squared for the first term, and the second term is 0. Okay. Okay. Now, for the most part, yeah, question.
How can you find YC?
How do you find it? Actually, in practice, it turns out to be very easy. So, let me give you a simple example. Let's say that you had 3 noise sources. I'll call it V1, V2, and I1, right? And let's say you calculate I in and it has only two noise sources. We'll call it beta 1 V1 plus beta 2 I2. So now you can clearly see that this is the correlated part, right? And this is the uncorrelated part. Okay? Okay, so the next topic we're going to tackle is what happens when you have feedback. How does this all change when you have feedback? And this is something we didn't talk about in 142, so I encourage you guys, 142 students, to pay attention. You can basically wake up now. All right, so what we'll find, this is just a quick summary, but we'll show this to you, is that if you have ideal feedback, it has no effect on the SNR. In other words, you know, same amplifier, same SNR, you add feedback around it, at the output you get the same SNR, so it has no practical effect. But if you look at real feedback networks, of course, we usually build them with resistors, and resistors have thermal noise. So the thermal noise of those resistors comes into play. In some cases, we may use active devices as part of our feedback network. Again, that will come into play. And so let's look into more detail on that. So here is kind of the very, very simple perspective of feedback. I have classical, you know, feedback system, forward gain, feedback, summing network. And now I just, let's say, introduce a voltage noise. And you stare at this for a while and you say, that has no effect. This voltage noise, I can move it. If I find the transfer function from here to the output, it's equivalent to the transfer function from here to the output. Therefore, I can just move the noise source to the input, and it has no effect on the circuit. Okay. Now, if that's not obvious to you, let's look at it in a little bit more detail. Let's take our two-port circuit. This is Vn squared, this is In squared, and this is the output. This is the input. And let me apply some feedback. For instance, let me apply some series feedback at the input. So this is a controlled source. Let's say it's a voltage source, beta times VO. So I have basically sampling the output voltage and subtracting it from the input voltage. So it's a voltage-voltage system. So now my input signal, so what I want to do is actually I want to represent this in the following manner. I want to find a new set V input squared, I input squared, which are now potentially different from these sources that are outside of my amplifier. In other words, I've moved this generator reference to ground inside. Now my amplifier is explicitly referenced to ground, right? The input now is from here. And I want to find the equivalent voltage and current. Okay? Now the way you do that is you basically play the same game that we played before. I short both inputs and I look at the output and so on and so forth. So let me short this input. If I short this input, then this current source basically will flow on the input network, so none of it gets into the output. And as far as this voltage source goes, the gain that it sees includes the series feedback, right? So the voltage gain from this source to the output, this guy goes away, so all I see is this two-port with this series feedback on it. Okay? Let's do the same thing over here. I ground the input, this current source goes away, this voltage source sees basically the two-port with the series feedback on it. And so that means that Vn squared is equal to Vi squared. Any questions about that? Okay, well, what if I take the open case? So I leave this open, this term goes away, and this current source basically injects a current here, and the current comes out here. And this voltage feedback has no effect on a current input, right? What about over here? This is I in, this is II. Again, VI squared has no effect, right, because it's dangling. And again, II current goes in this terminal, comes out of this terminal, and this series feedback has no effect on the input current, which tells me again that II is equal to IN squared. Okay? So we've shown very clearly that for this voltage feedback case, my equivalent noise generators can just be moved to the input unaltered. And I encourage you guys to redo this calculation for a couple other feedback configurations and confirm that this is true in general. Any kind of feedback. Shunt, 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 shunt series, series shunt, series series. Okay? Question?
The feedback change the optimal resistance for noise, minimum noise.
Does it change the optimal resistance? In this case, no, right? Because the ratio of VI to II is the same as the ratio of VN to IN, right? I mean, let me just qualify that by saying the concept of optimum source resistance only applies when you have generators outside, right? So we first have to move them outside. So it's not even really valid to compare. Even if these values had changed, it'd be apples to oranges kind of comparison. We'll see more examples of this when we talk about real feedback. Okay, so here's a real feedback situation, shunt feedback. So it's, again, let's look at this in a little bit more detail. It's worthwhile to take your time and to do this. At least a simple case we can do fairly quickly. So this is RF. So it's shunt feedback. That means I'm sampling the output voltage with respect to ground and feeding back a current, let's say IF. And unfortunately, this is a real resistor, so it has noise. So I call this IFB, so I can call this, well, I'll call this IRF. Okay? And like before, this is VN and IN. And what I'd like to do is to find an equivalent system that is noiseless but is again a series feedback system, shunt feedback, excuse me. And now my noise generators are totally outside of the feedback loop. So we'll call this VI and II. Okay? So let me make sure that this is clear. What I want to do is represent my system as an equivalent noiseless amplifier, right? Everything in here, this is a noiseless resistor. And now all the noise of everything up here is just represented by these two numbers, right? Okay, so let's find how this noise source alters the picture from the previous slide. Okay. All right, so let's short the input. Okay, if I short the input for my equivalent system here, you can see immediately, by definition, the input current is inactive, and so the output noise is now just the input noise, the equivalent input noise, times the closed loop gain of my system, right? Okay, how about over here? Over here, I short the input, and now what I can do is basically apply superposition. So for the moment, let's forget about this current source. Let me draw the picture over here. So the picture is I have Vn. I shorted the input. This is RF coming at the output. All right. So if you look at this picture, you can see the feedback is actually not doing anything, right? The feedback current is just flowing to ground. And so the output noise is just V in times the voltage gain, right? And this is the open loop voltage gain. I'll just say open. Likewise, now if I introduce this current, you can see that this current flows to ground through here, and over here, because this side is grounded, if this has a low output impedance, then practically this current source is also shorted, and it doesn't really influence the output, right? If I have finite output impedance, there is going to be a small voltage due to IRF. But basically, if this is a good shunt feedback system, it's by definition basically a good current input and a good voltage output, so it's a low source impedance. So let's neglect the effect of IRF. If I do that, then you can see that the input noise generator is essentially unaltered, right? Because that IF didn't really come into play. For both the equivalent system and the system with the extra noise generator, we get the same voltage gain. They both look open loop. Right. Let's go back and look at this picture. You see, actually, that doesn't make sense. Okay, yeah, they both are open loop, in fact. So I misspoke earlier. So when I said that this guy sees the closed loop gain, I was wrong. Okay, you guys should have pointed that out to me. Why is that? Anybody? I have RF, right? So I have RF here. And I have basically a VI. So the claim is that the output voltage is just the open loop voltage gain times VI. Right. Anybody want to contest that or substantiate that? Yes. Okay. Well, again, this goes back to, we can do this exactly, or we can do it kind of back of the envelope intuitively. This current has no effect on the input voltage, right? No matter what feedback current, I can have 1,000 amps coming back here, and it all flows to ground through this source. So if I'm concerned only with the voltage gain, no matter what the input impedance is, I've fixed the input voltage, right? And so then the output is just the open loop voltage gain, and the feedback is ineffective. So, you know, when you have feedback, it only applies to input currents, right, for this particular configuration. And so then this statement is correct, that the output voltage in both cases is just VI squared or VN squared times the voltage gain squared, which tells me that the equivalent input noise generator is the same for shunt feedback, right? What about the current? Well, okay, obviously the current is going to be different. So let's look at that. Okay, so this time I leave the input open circuit. And again, I keep explicitly putting in my ground here because this type of feedback assumes the output voltage is taken with respect to ground. Okay, well in this case, the input voltage doesn't do anything, and it's only the input current, and now it's the closed loop gain, right? So now I could say that Vout is In times the closed loop gain. And in this case, the closed loop gain is approximately minus RF, right, for negative feedback. And how about for the more complete circuit? So for the more complete circuit, I screwed up. Let me redraw it. So if you're ever drawing these pictures, first put in your sources. then put in the feedback. Okay, so this is I in, this is V in, this is the feedback, IRF, and now I'm leaving this side open. And so now we see that V in is actually important. We can't just throw it out. So without doing much math, you can intuitively see what's going to happen, right? So I in is for the most part going to flow into my amplifier, right? Because it has a low input impedance. That's the same can be said about IRF. Most of IRF is going to come and flow into my input amplifier, right? Some of it can go through RF, but in a well-designed shunt feedback system, the input impedance should be lower than RF. So for the most part, this current is going to see a low impedance through this path and back around through this path. So the only thing that's not really clear is what Vn does, right? So here I can write in this case that V output squared is basically IF squared, IRF squared, times closed loop gain squared times, let's say, alpha squared, where alpha is a current division ratio, right? It's basically how much current goes in here versus goes out here. And for a good system, you can assume that this is 1, right, to keep things simple. Also, the same thing can be said about IN. There's, again, a current division between the input impedance and this RF to the output. And again, so I'll have another alpha squared and another Z closed loop. And again, this, let's say, is 1 for simplicity. So the only thing we don't know is the transfer function from V in to the output. Let's call it H. Okay? And maybe if you're really good, you can see what H is. Can anybody see H by inspection? Yeah. That's right. That's right. That's exactly right. So if you don't see that, we'll do a couple lines of algebra to show that that's the case. So let's draw a very simplified equivalent circuit. I'm basically going to get rid of all voltage sources except what's relevant. So here, let's assume that the gain of the circuit, the open loop gain, is G times I in, where this is I in and this is Z in. And then I have my voltage source, this is RF, and this is V in. Okay? So if I want to calculate V out, well, it's just G times I in, and G, I in, is just V out minus V in over RF plus Z in, right? So it's V out minus V in divided by RF plus Z in. And I can move V out over here, so I have V out is 1 minus G RF plus Z in minus G V in divided by RF plus Z in. And if I divide, so V out transfer function H, which is V out over V in, is equal to G 1 minus G RF plus Z in, V in RF plus Z in. Well, what's this expression here? Look familiar? That's just the closed loop gain, right? This is the forward loop gain. This is the loop gain. G times beta, right? So this is just what we call Z closed loop. And so you can see that really, if I come back to this expression, H is just closed loop gain squared, just like here, plus this extra factor, 1 over RF plus Z in. And again, if this is a good amplifier, Z in should be smaller than RF, so really it's V in over RF.
Actually, in this equation, you kind of ignore the Z out, right?
I did ignore Z out, yeah. If you like, you can go home and do that. All right. So that means that if you go through and do all the, basically if you find now the equivalent voltage and current, so VI we showed is equal to Vn squared. In other words, shunt feedback doesn't alter the equivalent voltage squared, but it does affect, it does definitely affect the input current, first of all by the thermal noise of that resistance, and second by the voltage noise divided by RF squared. Okay? And again, if you assume RF is large, you might just neglect this term. And so then you have a very simple answer that the only thing you need to do when you have feedback is just include, when you have shunt feedback, that is, just include an extra noise generator. So II, Vin is the same, where II is approximately In plus IRF. In other words, the noise of this resistance. Okay? Now let me give you guys a big hint. If you're doing a final exam or if you're doing a prelim exam and you don't have time to work all this out, you can use a nice shortcut. Just think back to what the loading effect of the feedback network is on the input, all right? And make that loading effect noisy, and you're almost there. That's 90% of the answer, right? So in this case, kind of the shortcut hint is that what's the loading to the shunt feedback? Well, since I take the output in shunt, I should short the output to find the equivalent resistance of the feedback network. In this case, it just works out to RF. It's very simple. I make RF a noisy current because this is a shunt feedback system, and I have the answer. Okay. Let's, in fact, look at another system and jump directly to the shortcut. So here is a example with, again, I'm going to take a sample voltage of the output with respect to ground, but now I'm going to put a voltage in series with the input. So it's series shunt feedback. Okay, without doing any math, if we use this shortcut, the shortcut says what you should do is find out the equivalent loading, right? So let's draw a picture here. So let's call this RF, let's call this RE. Because the output is in, so this is in series on the input, shunt with the output, series shunt feedback, the equivalent loading, so this is the feedback network. To find the equivalent loading on the input, because it's shunt, I short, and so the equivalent loading is RE in parallel with RF. Okay? And because the input signal is a voltage, that means that I can represent this as a noiseless system. In is unaltered, and VI basically is equal to Vn squared plus the voltage noise of RE in parallel with RF. And I'm done. Okay. Now the next few pages is just some algebra to show that this is true, and I encourage you guys to work through it just to convince yourself that this works. So again, hopefully without doing any calculations, you can immediately conclude that the current is unaltered. Okay. And then you basically do the same trick. You do input open, input short. In this case, we do an input short. You can find the transfer function from each of these two generators to the output and sum it with the transfer function of this generator to the output, and you should find at the end of the day, when everything is said and done, this is the answer, that you have the input noise of your amplifier plus the input current of your amplifier times RE in parallel with RF plus the voltage noise of RE in parallel with RF. So that the shortcut didn't pick up this term, but it picked up this term. Okay. Again, if this is a good system, hopefully RE should be pretty small, and so this term will be negligible. RE in parallel with RF is roughly RE, which is a small number, and so this term should be negligible. questions or comments? Yes.
So the input impedance and the output impedance you use in these formulas, are they closed loop or open loop?
They are open loop. Yeah. Again, definitely don't want to bore you guys in this class. So we could spend the whole lecture doing the exact analysis. It's just a very quick and dirty analysis. But the good news is it gives you more or less the right result. Okay. All right. So here's the summary, and I think that I've already said this, so I'll go ahead and skip this slide. Actually, before I do that, let me take any questions on this. All right, so here's a couple of examples. These are actually even simpler than what we did right now. In this particular example, it's a non-inverting amplifier, and you just assume that the amplifier only has voltage noise. And basically, because this is a shunt series example, you know what the answer is going to be, right? You don't even have to do the algebra, but here's a couple lines of algebra that shows the equivalent input noise is Vn plus the noise of these two in parallel. And so you can go ahead and it's interesting, you can calculate the contribution of these resistors to the total noise. In this particular example, assume that you have a voltage gain of 10 and you've picked R2 to be 100K. Then you can calculate R1 by simply taking voltage gain minus 1, right? 1 plus R2 over R1 is the voltage gain. And then you find the equivalent noise just generated from this feedback resistor is actually 40 nanovolts per root hertz, thermal noise. So that's actually quite a lot of noise. And so if you need to get lower noise than this, you're going to have to use smaller resistors, right? And if you use smaller resistors, what does that mean? More power, right? You're going to have to burn more power. So right away you can see some very quick trade-offs. There's the same kind of analysis for an inverting amplifier. And what's interesting about this is that if you go through and you do the math, you'll see that in this particular case, R1 is effectively outside the feedback loop. So its noise transfer function is different from R2. Same kind of analysis that we did before, you can apply it and you get this answer that the equivalent noise of this system it's actually a nice expression. It says that it's 1 plus 1 over the gain, the voltage gain. So if you have a high voltage gain in this system, then you can essentially obtain the same noise performance as basically Vin, right? I should mention here that the noise of R1 and R2 has been neglected. So this is a very simple calculation. On the other hand, if you don't have high gain, then this noise term is going to hurt you. So if you just have a gain of -1, you double the noise, right? Vn gets twice as large. Okay. The reason that we can neglect the noise of R1 and R2 is, as we'll see later on, we could replace these things with capacitors, which don't have noise, which makes this result more relevant. All right, so speaking of capacitors, we need to look at a very important result that some of you may have seen before, some of you may have not. It's a little bit surprising, but it's a really, really nice result. And this is the question. So the question is, let's say I have a circuit that's very simple. It's an R and a C circuit. And what I'd like to know is, let's say I excite it with some input voltage, and I examine the output voltage. Now you guys know that if you wait long enough, the output will, if the input has a step or some kind of complicated waveform, the output will eventually settle to the input value given enough time, right? So this voltage over infinite time, this becomes an open circuit, and so the voltage here is the same as the input. Great. In other words, this circuit will take a snapshot of this voltage and store it on this capacitor. Okay? And the way we would do that in practice is actually, instead of using a resistor, we'd use a switch. So what you would do is, let's say at a particular time instant, let's say time t is equal to t1, I want to sample this voltage onto this capacitor. Okay? And so I close this switch. Switch has some on resistance, current flows, and this voltage, if this voltage doesn't change too much, and this, based on the settling time of this circuit, let's say this circuit settles much faster than the input changes, then for the most part this voltage gets copied onto this capacitor, and now I have a analog memory. I've got a copy of that voltage on this capacitor that I can use to process. Of course, this is very important in circuits that are operating in discrete time. Okay, and you might ask, well, why operate in discrete time? One quick motivation I can give you is that most systems we build today have a digital back end, right? That means that eventually I'm going to sample my signal. So for all practical purposes, at the end of the day, it's discrete time and discrete voltage, right? Now if I'm doing analog signal processing, why not just sample earlier? If I can show you that it's beneficial to sample earlier in the stream, right? By the stream, I mean you have basically your analog blocks, right? This might be a bunch of amplifiers. And then I have my digital blocks. So basically I would have an analog to digital converter. Actually, I drew it backwards. And here's a bunch of bits coming out. And I take these bits and I do lots of signal processing on them. So the idea is that I don't need a continuous time signal. I just need samples that are taken. Basically, at the end of the day, I need at most the number of samples that I'm sampling here. So let's say I'm sampling at a megahertz. So by the end of the day, I need analog signals coming into this ADC every microsecond. And if I can show you that working with discrete time in analog domain is beneficial, then I should actually do that, right? I should discretize my signal. So this is essentially how I'm going to discretize my signal. At some point, I'm going to take an analog continuous time signal, sample it onto a capacitor, and then I can play around with this voltage on this capacitor, and it represents a discrete sample of the input signal. Okay? The question is, what are the noise implications of doing this sampling? Okay? So this circuit is called a sample and hold for very obvious reasons. How much noise am I going to have on this capacitor? In other words, let's say this voltage is a volt at the moment I sample it. So this is going to be 1 volt plus some noise. Now it's just simply a noise voltage. So my noise process goes from this complicated Wiener Brownian motion process to a discrete, basically just discrete random variables. At each time point, the noise might be a microvolt, might be 3 microvolts, might be minus 2 microvolts, right? It's just a number. So the critical question is, how big is the noise variance, right? Again, it's going to be a Gaussian, but I can track down its variance by doing a simple calculation. And the way you do this calculation is you assume, for simplicity, that the circuit settles completely. In other words, you have an infinite amount of time to wait to sample the input voltage, and that means that you're going to sample the input noise due to this resistor over all frequencies, right? So to calculate the noise, I'm going to take 4kTr, noise of this resistor, and integrate from basically 0 to infinity the transfer function, which is 1 over 1 plus j omega rc squared d omega. That makes sense to everybody? The setup of the problem? Okay. Now here's the surprising result. The surprising result is you do this integral and the answer comes out to kt over c. Okay? So the first time you do this integral, you say, oh, I screwed up. R dropped out. Why did R drop out? Clearly the noise is due to R, right? So R's got to be in there. So then you do the calculation again, this time a little more carefully, R drops out. Then you do it again. And then you say, okay, I'm just really stupid today. I'm going to run Mathematica and I'll have it do it for me. Ah, there's no R. So what's going on? It's actually kind of surprising. The actual noise variance doesn't depend on R, so it doesn't depend on what switch you use. It just depends on the capacitance. The bigger the capacitance, the less noise. And the argument of why that happens is that as R gets bigger, sure, you have more voltage noise, but the circuit is more narrowband. And so this integral basically dies off faster. I think I have a graphical representation of that. So here are two circuits. One is a 1 kilo ohm resistor, another one's a 100 kilo ohm resistor, but the capacitors are the same, 1 picofarad. So this is a running integral of basically, you can see they both eventually settle to 64 microvolts. This is the noise transfer function of the first circuit, right? And this is the noise transfer function of, actually this is the noise transfer function of this first circuit. This is the noise transfer function of this circuit. This is more narrow band, so even though the noise is higher, it starts dropping faster. So at the end of the day, when you run this integral, it starts converging right around here. The second circuit, the integral is getting bigger, 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 and it saturates at some point. But at the end of the day, they both saturate to the same value of 64 microvolts. And that's a nice number to keep around. 1 picofarad, 64 microvolts. All right. So in the course of doing this integral, we actually made use of this result, that if you take the integral of this function from 0 to infinity, you get omega naught over 4. Okay? So this is a nice, useful integral to keep in mind. Another nice, useful integral is, what if you have a resonant circuit, and basically with a Q given by nothing but Q, do the integral, you get almost the same answer. So the bandwidth of the circuit is the same, you just get a Q factor enhancement in the noise. So around, because it's peaky, you pick up a little bit of extra noise. Okay? So any questions about this result? Okay, so here is a numerical example, a very simple one. It's a common source amplifier. So the idea is that, let's switch to paper. Thanks. So I have a common source amplifier, and it has some load. We'll call this RL. And it has some output capacitance, CL. And again, what I would like to do is assume that I take the input voltage, amplify it, and then sample it onto this capacitor, right? So what I'd like to do is find the total noise at the output and then integrate it over 0 to infinity to find the noise. And what we're going to hope is that the result is approximately KT over C times some little NF, some extra factor that accounts for the extra noise due to this amplifier. Okay? So let's just do the math. It's actually very simple. So if I look at the noise at the output, it's just the current noise, right? I have the thermal noise of the transistor, roughly 2/3 GM, right? Or gamma GM if you want to be more exact. And then I have the noise of the load, 1 over RL. And all of that gets transferred by the same low-pass transfer characteristic, right? All of it flows into RL, but then we have this pole occurring at frequency RL-CL. Okay? And so all I need to do now to find the total noise is integrate this expression from 0 to infinity and use that integral that we just looked at, and we get this expression. And so now my goal is to show this expression as KT over C times something. So I'm going to factor some terms out. I pull out my KT term, and I pull out my C term, and I multiply through the rest of the terms. Right away you can see that here this RL cancels, and I take this RL inside, I just get 1. And the second term, if I take the RL inside, I get GM times RL, which, hey, that's nice because that's the voltage gain. So my answer, simplified at the end of the day, is the noise is KT over C times 1 plus 2/3 the voltage gain, absolute value. That's a very nice answer, right? Very nice, simple, intuitive answer. Tells you the effect of adding this amplifier in your sampling system is to increase the noise by roughly the voltage gain, right? So here's a SPICE example. Basically use this formula and then compare it to SPICE. The result is identical as you would expect. Here the voltage gain is 2. It's a 2 kilo ohm source, and it's a 1 picofarad capacitance again. So instead of getting 64 microvolts, you get 64 times 1 plus the voltage gain, which in this case is only 2. So it's 2 times 2/3 or 4/3. So you get about 100 microvolts of noise. Okay, Debo has a question.
So in the previous common source amplifier, at the output, was the sampling switch necessary to get that result? Like even if
No. So the idea is that eventually I'm going to sample. So I'm interested in the noise at all frequencies. So now I'm very interested in the total noise at the output. And so this is why I integrate. Because eventually when I sample it, I'm going to get all that noise. Okay.
Yeah, I have a question because practically you can't sample from 0 to infinity frequency. We certainly have a interest frequency. Does that kind of have some relationship between the pole?
Let's go back to this integral, and I think the answer is here, right? So if you look at this, as long as you wait long enough, right, so this integral to converge, then the answer is going to be more or less right on, right? So if this, for this first case, the integral converges at around a megahertz, right? So if I sample at 0.1 microseconds, right, for all practical purposes, that's more than enough time. Or I'm sorry, let's say 10 microseconds, the other way around. Okay. Okay, and then this is just running SPICE, and again it matches up very nicely. You get about 100 microvolts as you would expect. Okay, so the last 7 or 8 minutes of the class, I want to talk about an important concept of if you look at most papers, especially when you look at A to D converters, instead of talking about signal-noise ratio, they talk about bits. So I want to talk about where this terminology comes from. Before we do that, though, let's talk about SNR. Okay, I'm jumping ahead a little bit. So SNR is, as I've said over and over again, it's very important. It's a ratio of how much signal power you have to how much noise power you have, right? And just intuitively, right, if you're doing measurements and the signal is 10 times bigger than the noise, you feel pretty comfortable that this is, pretty good. How comfortable do you feel? Well, you have to go, it's a qualitative thing. You have to go ask a lot of people. Does this picture look nice to you? Is it okay? Is it acceptable? No. Why? It's too grainy. No, I don't like the color. So that depends on SNR, right? So your TV, your monitor has a certain SNR. It would be really nice to know what the SNR is, right? If they publish that spec, because then you wouldn't have to go and look at 100 different monitors to decide which one you want. But they don't, obviously. They don't tell you. So if I'm designing one issue is if I'm designing an analog circuit to drive this monitor, I want to make sure that all the analog blocks preserve the SNR signal of the signal to be much better than the final SNR that you're going to view, or a little bit better, right? I want some margin. So if I corrupt my signal before it even gets to the monitor, basically you should fire me. You say, that's terrible. I spent 5 years to come up with a monitor that has 50 dB SNR, and then you give me an analog signal with 10 dB SNR, you're fired, right? Get out of here. So it's very important to know the SNR of your analog signal, and it's simply a ratio of your signal to noise power. So let's say for the particular example that we just did before, the noise power we find out is KT over C, right, times NF. And let's just take NF equal to 1, and let's take C equal to 1 picofarad, so it's 64 microvolts. So what happens if I deliver a signal to you that has 1 volt amplitude? It's actually a pretty healthy signal, right? Calculate the SNR, signal power, noise power, that's 81 dB. It's a very healthy signal, right? Noise is much, much smaller than the signal. And what's really important about this result is the SNR is directly a function of capacitance, right? If I double my capacitance, my SNR improves by 4, right? Because basically, in this expression, so the noise voltage is just KT over C. The signal is constant, so actually it tracks with C. So I misspoke. This is noise voltage squared. So that means that if slide was misleading. If I take the capacitance up by a factor of 4, my SNR improves by 6 dB. Okay, so capacitance is very important, and that also means that the higher the capacitance, the more power I'm going to need to drive it in a fixed interval of time. So in analog circuits, there's really a heavy trade-off between power and SNR, and it's almost inevitable, right? This is as simple as you could get in terms of a calculation. It tells you that even ignoring all the details of your amplifier, at the end of the day, the more SNR you want, the more capacitance you have to have. And as you guys all know, the more capacitance you have, the more current you have to burn to keep the bandwidth constant, right? Now, this is what I was talking about earlier. If you go look at papers, a lot of times instead of talking about SNR, people talk about bits. They say this circuit is 13 bits, this circuit is 8 bits. Well, what does that mean? Well, the reason that the terminology bits is so convenient is ultimately the signal is going to get digitized, right? And the circuit that digitizes A to D converter will have a certain resolution, right? 10 bits, 12 bits. The process of quantizing a signal introduces noise. Call that quantization noise, right? Why? Well, it's, here's a signal that's varying continuously, and what I'm doing is I have bins, and I say the signal has to fall into one of these bins. Depending on the statistics of the signal, I may have uniform bins, or I might have like some kind of logarithmically compressed bin. But let's take the simple case and the most common case of just a uniform bin. So then when my signal is over here, I have to either assign it to this bin or this bin, right? And that means that I've introduced noise, delta, into my signal. And every time I sample, unless I get lucky and I just happen to fall into one of the bins exactly, I'm going to have an error. So the error associated, if you assume, this very simple example, if you assume that this delta function is a uniform random variable from 0 to peak value 1 over 2 to the n, where n is the number of bits you have, then if it's a uniform random variable, the variance works out to delta squared over 12. Delta squared over 12. So that means that it looks like the noise variance I add due to quantization, let's go back to the slide, is basically the quantizer step size, which is delta squared over 12. Okay? So this is the noise that I'm going to add to my signal no matter what. Well, what's my signal level? Well, my signal level has to at most be the biggest size, right, in my quantizer. The maximum size signal is 2 to the n times the size of a quantizer. So if I work out the math, if I take my signal power here and divide it by the noise power, at the end of the day you get this nice expression which tells you that the SNR that you end up with is, ignore this term, about roughly 6 dB per bit, which again makes perfect sense, right? Every bit you add doubles your signal size, right? And that means you get another 6 dB. So it's really 6.02, and there's this one constant term, but other than that, give or take, you have, for every bit you add to your quantizer, you pick up 6 dB. So now this equation is very useful because if someone tells you I have 80 dB SNR, you can translate that into n number of bits. And actually, here's a few examples. Let's maybe use an example that's pre-calculated for me. Let's say someone tells you have 50 dB SNR. That's equivalent to 8 bits. So if you're going into a 7-bit ADC and your analog circuits all have 50 bits SNR, you're in good shape, right? You have 10 dB of margin, and you're not going to be introducing any more noise than the actual quantization step. Okay? All right, so we'll stop there.